Yeah, so I'll be talking about how my own field of mathematics is changing or beginning to change in the age of AI, and maybe how it will impact the other sciences as well. But it's an age of change and uncertainty, which is something that we're not really used to in my field. We are maybe one of the most conservative fields as far as change is concerned. In that we really haven't changed our practices in so many ways for centuries. On the left here, I'm displaying a textbook by Cauchy from exactly 200 years ago, introducing what we now call the Cauchy integral formula, among other things. And you probably can't read it at that resolution, but it looks almost identical to a textbook we would give our graduate students today. I mean, other than it's in French rather than English, and it's not typeset using a modern computer language, typesetting language. But other than that, it's completely usable today. And that continuity of mathematics is a great strength of mathematics. We use results that are 200 years old, 2,000 years old. I use the Pythagorean theorem routinely in my own work. And that's fantastic. But it does mean that we often do not embrace trends as much as other disciplines. On the right is a coffee table book by a photographer, Jessica Wynn. So she was fascinated by the chalkboards that mathematicians use. So we're almost the only academic discipline left that still holds on to the blackboards and chalk. Everyone else moved on to PowerPoints and whiteboards and whatever. But we still, I have 6 blackboards in my own office. I love them. I will not give them up. But she actually took photographs of mathematicians' chalkboards and made a nice little art coffee book out of it. Another way in which we are different from the other sciences is that we often don't collaborate. So here is just scientific metrics of how many collaborators we've had, on average over the years, and it's sort of slowly gone up from say 1.5 authors per paper to 2.5 in mathematics. But you look at the other sciences, and they are exploding. They're embracing big collaborative research projects, and mathematicians are lagging way behind. Now, it's not because we're antisocial, or not just because we're antisocial. There are systemic issues. So math projects traditionally have a high barrier to entry. You often need a math PhD to even understand the problem you're working on. We need our proofs to be 100% correct in every single detail. So if you try to crowdsource a proof and there's 100 contributions and one of them is incorrect, you destroy the whole proof. And the workflows we have, for example, working things out together at a blackboard with chalk don't scale to 100 people over the internet. But the other sciences are doing that and they're flourishing. So, are we missing out? So it is beginning to change because of new technologies, including AI, although AI, I think, is just a part of it. We are beginning to figure out how to do large-scale projects. So if you like, most of mathematics until very recently has been sort of case studies where you take one problem and you work on it for several months and you produce one report on one problem and then you move on to the next problem. But we're beginning to do surveys where we can study hundreds or thousands of problems at once. We maybe can't solve all of them, but we can report various interesting statistics about these populations of problems. We're beginning to broaden up our participation beyond sort of the math PhD set. So citizen science is flourishing in other disciplines. We're just beginning to have citizen mathematics happen. And we are, it's just on the verge of happening, but we are beginning to figure out how to properly use machine learning and AI to actually help us. We've discovered lots of incorrect ways to use machine learning and AI, but we're just beginning to get some useful mileage out of these tools. There's one secret sauce that makes this all work, which is formal verification. So this is a special type of computer language which, roughly speaking, can take a mathematical argument and check if it's correct or not automatically. This reduces it filters out a lot of rubbish, which was previously blocking these kind of new workflows from happening. So there are many, many examples of this now. I only have time to give 1.5 examples in this presentation. So the first example is something that I launched last year at UCLA. It's something called the Equational Theories Project, and it's something I did with 50 collaborators, most of whom I actually didn't meet. I only met through this project. And most of them are not actually professional mathematicians. A lot of computer scientists, students, grad students, undergraduates, I think even some high school students, they just got involved in this open collaborative project. It's a project in algebra. I don't have time to actually tell you what the project is, but there's we sort of procedurally generated 22 million problems in algebra. So a typical one is does the commutative law imply the associative law? If you have an operation such that A times B is the same as B times A, can you deduce that A times B times C is the same as A times B times C? Turns out the answer is no. But we generated 22 million questions of this form. Any individual question, maybe a grad student in algebra could sit down for an hour and work out yes or no, it's true, but there's 22 million of them. I don't have 22 million grad students. So you could say, oh, let's crowdsource this. Let's open this up. Let's get the general public to contribute. But then someone has to grade 22 million algebra problems. I also don't have time for that. So these projects were basically not possible in the past. I mean, the previous examples of this type of project I could find in the literature sort of classified 20 problems, and did a study. Okay, but this is 22 million. But we managed to complete this project in 3 months. Every single one of these statements, we have a proof or disproof whether it's true or false. So we had to sort of invent new workflows to do this. We have a big GitHub where we store all the proofs, and they have to be formalized in a common language so that we can verify them automatically. We used the proof assistant language Lean for this. We had a very active discussion board where we had both human-generated proofs. Someone would pick one of these 22 million implications and prove it, post it, and then other people would try to copy it. People would run computer programs to generate, to see, they would attack all 22 million of the problems, and maybe the program can handle 100,000 of them at a time. And people would go back and forth, maybe converting a human proof into a Lean proof or a computer proof into a human proof. Lots and lots of back and forth, which we kind of improvised, but it worked really well. I think there are several factors that made this particular project successful. One was that it was very modular. So by its nature, it broke up into 22 million related problems, and so people could sort of claim some subgroup of these problems and work on those, or maybe some people would specialize in writing human readable proofs, and the other ones would specialize in translating those into a computer readable proof. You didn't have to be to know every single part of the project. You could specialize in just one aspect, much like in a modern software development project, for instance. Another thing that really helped was that we had a good metric. We had talks earlier about how once you have a goal and sort of a set score, a loss function, if you wish, that you can start optimizing on, then that really sort of opens up new ways to run a project. So at any given point in the project, say on the 16th day, there were these 22 million implications. It turns out that on day 16, we had already cleared out all of them, like we resolved all of them except for 888. And then, so people would claim some subset of those and work on those. This allowed for people, the project to decentralize. So spontaneously, some participants would just sort of work on some idea, and if it worked, it would add some more implications to the database, and this number would go down. And so everyone was just working to move the needle, and some ideas pushed this number down a lot, and some didn't weren't so successful. But we didn't have to coordinate. You do this, you do that. I mean, we did some task allocation, but there was also a lot of spontaneous sort of independent activity by participants, which was really quite fun to watch, actually. And then the final secret ingredient that I said was formal verification. And the key to this is that it breaks the trust barrier. So previously in mathematics, if you want to collaborate with other people, you either have to check every line of what they submit, or you have to trust that what they do, that they have a good enough reputation, that probably their work is high quality enough that it should go into your paper. But we were getting submissions from all kinds of people that we'd never met before, but they all had to pass through this formal verification. And so we could accept anonymous contributions or untrusted contributions. You could really, because of the way this formal verification works, you could have really precise discussions like, So someone tries a proof and say a human proof, and then they try to convert it into lean, and the proof has 9 steps, and 8 of them work fine, and then there's this one step that doesn't quite formalize properly, but then you can have a discussion with that human author. There's one very, very precise micro step that needs clarification. And this is a kind of discussion that you can do without lean, but often you have to spend lots of time specifying what's the notation, what's the common language. Sometimes people don't quite understand why you're stuck on this one step if you can't specify exactly what that step is. But these languages allow for extremely precise technical conversations at a very atomic scale. And you don't need to understand the entire project in order to proceed. Okay, so that's one of the projects. Okay, yeah, and while we did use some moderately fancy AI, most particularly these things called automated theorem provers, actually it was the more mundane technologies. I think that's just like GitHub and this discussion group at Zulip, just basic collaboration platforms were just incredibly useful and essential. Okay, so that was one of the examples. I have time for half an example. It's work in progress in collaboration with Google DeepMind, but I was hoping to announce it, but they're still going through the approval process, the paper. So I can't tell you exactly what we've done, but I can tell you in broad terms what Google has some prior work. So large language models are becoming increasingly powerful. They can solve Olympiad problems. They can sometimes answer quite deep math questions, but they make mistakes, and it's really and often at really basic mistakes. So even the latest models, you ask it a simple arithmetic question, and sometimes it will get the arithmetic right, and sometimes it won't. Here's one where it got 7 times 4 plus 8 times 8 wrong, and then it was called out, and then they apologized, and actually it gave the right answer eventually. So every mathematician has tried using these and has eventually found that the unreliability is just too great of an issue. But if you can combine these unreliable outputs with a verifier, something that can actually check whether your output is good or not, then it becomes useful, at least potentially. And sometimes you can make it go in a loop. So you make the LLM generate mathematical output, you test it. If it works, great. If it doesn't work, you send the error messages back to the LLM, and it tries to correct it. Many people have tried ways to make this work, and with various degrees of success. I've been working with DeepMind on their latest tool of this type. It's called AlphaEvolve. There are other things. There's also a genetic algorithm under the hood, but this has been somewhat promising. So it's already been able to solve certain classes of math problems. So we released a preliminary paper a few months ago where we managed to improve various bounds on things like packing problems. So these are sort of toy examples of math problems. Things like if you have 11 hexagons, what's the smallest hexagon that can contain all 11 at once? And there were previous records on what the best packings were. And by having the LLM try random things, get feedback, evolve the code, they were able to get numerical improvements. These by themselves are just sort of test cases. These are kind of finite dimensional optimization problems, which are just a very small subclass of all the math problems that we care about. But we have some recent progress on also working on infinite dimensional optimization problems. But unfortunately, I can't tell you more about them just yet. But stay tuned. In a few weeks, we will get a paper out. So just to wrap up, so these tools, I think they're just beginning to transform our profession. They're already helping in many ways. I and many others use AI routinely for secondary tasks. Writing computer code is so much easier now. Performing literature review, I think this was also mentioned as already a very useful use case right now. There are isolated examples of feeding data sets to AI and getting new interesting mathematical conjectures and finding new patterns. We can't do that systematically yet, but there are isolated proofs of concept. And they're a good kind of universal translator. I think it has helped the general public. We can communicate with the general public or with other scientists because our jargon is not quite the same as their jargon, but we can now translate more effectively with AI. So there are already many decent use cases of AI currently. But we are going to get the more advanced applications, we really need to rely on rigorous verification to filter our use. So basically, we can only use the AI as far as you can trust its outputs, or at least check them. Any further, and it's just too risky. I think they can help individual mathematicians somewhat, but I think they'll be most effective when combined as part of a broader collaboration. They can fill in all the gaps that the collaboration is missing. I also think that the most obvious use case of AI for these is to sort of kind of replace mathematicians doing what they do best, which is work on hard problems with creative new techniques. But there's actually an orthogonal use of AI, which I think will be much more productive, at least in the medium term, which is that there's this long tail of medium difficulty problems, like these 22 million algebra problems, which we just don't have the manpower to attack with humans. But we can get AIs to do a first pass through them, prove all the low-hanging fruit, and then escalate any difficult problems up to human experts. We've also seen people in the panels discuss that kind of paradigm. In general, I think AI should be used to not compete with the pie of work to do that humans already do, but to enlarge the pie and create more tasks. That what was the phrase that I think make more objectives economically feasible. So there are a lot of promising applications, but it's very, very situational. It's not just a plug and play. We have to know how to use it and when to use it. So thank you very much.